Before we start talking about shear force and bending moments, there are few very important concepts that we must cover first. I'm pretty sure that most of you are aware of this, especially civil and mechanical engineers, but we are going to go through them again as a quick reminder, and for other disciplines engineers, here with us. First, we need to differentiate between two different types of loads, which are concentrated loads and distributed loads. Concentrated loads are loads acting on a very small area that we consider the area of contact to be just a point, while distributed loads are loads spread across a whole member or a whole region. It is to be noted that we can deal directly with distributed loads, and that's why, in order to analyze any distributed load, we need to calculate two main things, which are the resultant force and the location of the effect of this resultant force. The value of the resultant load is simply calculated as the area of this load, while the point of the effect is the centroid of this shape. In figure number 1, here we have the most common type of distributed load, which are uniform distributed loads in a shape of rectangle. In order to calculate the value of R, which is the resultant force, it will equal to W, which is the value of the distributed load, multiplied by L, which is the length under the effect of this load. And the location of the resultant will be exactly in the middle, because this is the centroid of a rectangle shape. In figure 2, we can see a triangle distributed load. The value of R will be W multiplied by L multiplied by 0.5, because this is an area of a triangle, and the location of the resultant will be L over 3 from the side of the triangle base. In figure 3, we can see a trapezoidal shape distributed load. In order to analyze this shape, we will first need to divide it into two shapes to make it easier to calculate, which are rectangle and the triangle shape, as we can see here. The resultant load and the location of the resultant of each shape will be calculated as we have earlier explained in figure number 1 and 2. Beams could be supported in different ways. We have roller, bend, or fixed supports. Each one of those supports restrains the structural beam differently. Bend supports restrain vertical and horizontal displacement, however they allow rotation. Roller supports restrain only vertical displacement, while they allow horizontal displacement and rotation. While fixed supports totally fix the beam, and they prevent all vertical and horizontal displacement as well as the rotation. For any restrained movement, we will have a corresponding reaction, which means that for the roller, we have only a vertical reaction, while for the bend support, we will have a vertical and horizontal reaction, and finally for the fixed supports, we are going to have vertical and horizontal reaction as well as moment reaction to correspond for the restrained rotation. When a beam is loaded, internal forces are created inside the beam section to maintain equilibrium. Those forces could be divided into two main components. We have shear forces, which are in the vertical direction, and we have normal forces, which are in the longitudinal direction of the beam. If the load is trying to make the beam concave downward, as we can see here, it means that the top parts of the beam is trying to get shorter, while the bottom part of the beam is trying to get longer, which means that the normal forces in the top part of the beam will be compression, while the normal forces in the bottom part of the beam will be tension. Both of these compression and tension forces are equal, so the beam remains in equilibrium. However, it means that they will create a moment around the centroid of the beam section, and those are what we call the internal forces of the beam, which are the shear forces and the bending moment. There are three main steps to be able to draw the shear force diagram and the bending moment diagram, which are as following. Step number 1, we have to draw the free body diagram of the beam. In the free body diagram, we just show all the forces and reaction of the beam, including their direction. As we can see here, we replace the bend support with vertical and horizontal reaction, and we replace the roller with a vertical reaction. Next step, we have to calculate the reaction forces of all support, and in order to do this, we use the concept of equilibrium. In order for the system to stay in equilibrium, all of the vertical and horizontal forces has to cancel each other. The same thing goes for all of the moment on the beam. Hence, we can use equilibrium equations at any point to obtain support reactions. Equilibrium equations are the following. Sigma F vertical equals 0, sigma F horizontal equals 0, and sigma moments equals 0. Once we have calculated all of the supports reaction, now we can start in the third and the last step, which is to calculate the internal shear forces and bending moments at every section of the beam. We will start once we have all the supports reaction as agreed, then we will choose one side and cut the beam, and calculate the shear force and bending moment using the equilibrium equations. We normally choose the free side of the beam to make the calculation easier. We keep moving towards the other side of the beam, and we will repeat the same cut and calculation of the forces again. We will keep repeating the same till we have the full shear force diagram and bending moment diagram. Last concept we need to discuss is the signs conventions we are going to use for loads and internal forces. Positive directions are as shown in this picture here. External loads going downward are positive, while external loads going upward will be negative. Shear forces that are going downward in the left side of the beam or upward in the right side of the beam are considered to be positive directions, while bending moments that cause compression in the top part of the beam and tension in the bottom part of the beam are the positive directions. You can think of it as the moments that are trying to concave the beam downward are positive, while moments are trying to concave the beam upward are negative. Shear force diagram and bending moment diagrams are graphical representations for the internal forces inside a beam. Here we can see a sample for the shear force diagram and bending moment diagram for typical forms of loading. In case of concentrated force in the middle of the beam, the shear force will be in this shape with value of PL over 2 on each side, and the bending moment will be in this shape with value of PL over 4. If the force is not exactly in the middle of the beam, then the reactions could be calculated and the bending moment will be calculated as we learned earlier in this lecture. In case of constant distributed load, the shear force will be in this shape with value of WL over 2 on each side, and the bending moment diagram will be on a shape of parabola with value of WL square over 8. In case of triangular distributed load, the shear force will be in this shape, in a shape of parabola, while the bending moment will be in a cubic shape. So now, let's have a couple of examples of this.